So atomic radius is nothing but distance between the center of the nucleus to the outermost shell where the electrons are present. At least one electron should be there, then only we can consider that shell. Next one, this atomic radius, since it is very small, we measure in terms of angstrom unit. Angstrom units. Unit of atomic radius. 1 angstrom unit. Next one. So since atoms are very small, and they are also less stable, they can't exist independently. Most of the atoms cannot exist independently. So we can't find out atomic radius directly by taking atom. So in molecular form only we will measure atomic radius. So there are different types of atomic radius because based on the nature of the elements. First one is covalent radius. Covalent radius. Covalent radius. Covalent radius means, see students, covalent bond will be formed like this. Covalent bond. Okay, this is the nucleus of one atom. This is the nucleus of one atom. This is the internuclear distance. This together. Then, if you make it half, then you will get covalent radius of one atom. Covalent radius of one atom. So how can we define this? This is a covalently bonded molecule, and the half of the internuclear distance between the two atoms of covalently bonded molecule, or two covalently bonded atoms in a molecule. Okay, we'll write defined as half of the between two atoms in a covalently bonded molecule. Covalently bonded molecule. So generally non-metals forms covalent bond, isn't it? So this atomic radius is used. This covalent radius is used for measuring atomic radius of non-metals. Measuring atomic radius of non-metals. Radius of non-metals. This is about covalent radius. Next one, van der Waals radius. Van der Waals radius. See students, here is like a physical attraction, physical force of attraction. See, students, here two molecules are there, two adjacent atoms. Internuclear distance between two adjacent atoms of two covalently bonded neighboring molecules. If you see, this is one molecule, this is one molecule, there won't be any bond between these two molecules, just some attractions will start. So here you may get doubt, sir, which we can keep this much distance, any distance we can keep? No, you can't keep like that. You have to bring the two molecules close to each other, uh, till which extent, where the attraction starts. So there's some attractions will start between two atoms of two neighboring molecules. Till that extent, you have to bring close to each other. Then you just make it half. That internuclear distance, you make it half. This is van der Waals radius, because officially no bond between these two molecules. So just where the attraction starts, till that extent you have to bring close to two molecules close to each other. Okay, this is a half of the internuclear distance between two atoms of two neighboring covalently bonded molecules. Two atoms of two neighboring covalently bonded molecules. Okay, students, these definitions and all they won't ask, but comparison they may ask. Generally, this van der Waals radius is used for the measuring non-reactive gases or inert gases, noble gases. We can use this method because they won't form chemical bonds molecule. This van der Waals radius is used for non-reacting gases. Non-reacting gases. Non-reacting gases. Noble gases also. Next, one more, metallic radius. Metallic radius. Just if I draw the diagram, you can make out easily. Sorry. Here, if you observe, here just atoms are just touch each other. They won't overlap like covalently bonded atoms. They just touch each other. You can write it just adjacent atoms. It is the half of the internuclear distance between two adjacent metal atoms in a lattice. Half of the distance between of the internuclear distance between two adjacent metal atoms in metal lattice. This is about metallic radius. Metallic radius. So if you observe covalent radius, van der Waals radius, metallic radius. Covalent radius, what happens? Atoms are merging each other, submerging each other. In van der Waals radius, there is no bond only. In metallic radius, just atoms are coming close to each other compared to van der Waals radius is somewhat better. So if you compare atomic radius, which atomic radius will be more? Order of atomic radii they are asking. It's very, very important, students. So among all the radius, covalent radius is very small. Covalent radius, metallic radius, van der Waals radius. So increase. Covalent to van der Waals radius increase. Increase. This order is important. Students. So here metallic radius is used for metals. Measuring atomic radius of metals. Next one, ionic radius. Ionic radius. Nothing is there. Distance between center of the nucleus to the outermost shell of ion. This is the atomic radius of lithium. Beryllium, little it will come down. Boron, still it comes down. Carbon. Like this atomic radius goes on because here as we move from left to right in a period, from left to right atomic number increasing. Atomic number is increasing. As atomic number increases, number of electrons increases, number of protons also increases, but shell number remains same. Particular period has particular number of shells only. Second period if you take, there will be only 2 shells. There are 2 shells in second period. There are 3 shells in third period. Shell number remains same, but number of protons are increasing. As number of protons increases and atomic number of shells remains same, that time effective nuclear charge over valence electrons will be more. So they pull electrons towards self. So size of atom gradually decreases. Effective nuclear charge increase on valence electrons. In a period, number of shells remains same. Number of shells remains same. As atomic number increases, force of attraction on valence electrons increases. So atomic radius decreases. As we move from left to right, atomic radius decreases due to increase in effective nuclear charge. Z effective also will. Next, so what how to write conclusion? Atomic radius decreases from left to right as number of shells remain same. Shells remain same and number of protons is atomic radius decrease. This is also called effective nuclear charge. As effective nuclear charge increases, atomic radius decreases. Number of shells remain same, number of protons increases. So you can write Z effective increase, atomic radius decrease. This is the reason. Z effective is inversely proportional to atomic radius. Next is a heading in a group. Group. Here also we'll select one group. Lithium, sodium, potassium, rubidium, cesium and francium. 3, 11 atomic numbers 19, 37 like that we'll get. So electronic configuration 1s2, 2s1, 1s2, 2s2, 2p6, 3s1. Here 1s2, 2s2, 2p6, 3s2, 3p6 4s1. So here if you observe 2s1, 3s1, 4s1, next will be 5s1. If you see from top to bottom, number of shells is increasing. See, here only 2 shells, here 3 shells, here 4 shells. Number of shells increases. Automatically atomic radius increases. See, atomic radius increases as number of shells increase. Right now, atomic radius increase from top to bottom. Since number of shells from top to bottom, as the number of shells increases, atomic radius increases. Top to bottom. Okay. Next is heading ionization energy. Next. Ionization energy. Ionization energy. What is ionization energy? See students, this is the atom. This has some electrons. Atom has electrons. So in first shell there are some electrons, second shell there are electrons, third shell there are electrons. I want to remove electron. From which shell I can remove electron easily? Outermost shell, because it is far from the nucleus. One thing. So electron, I want to create atom to ion. I want to create ion. I want to produce ion. I want to convert atom into ionic form by removing electron or by adding electron. But in this case, removal of electron only. Okay. So here removal of electron, why it is easy? Removal of outermost electron is easy compared to removal of inner electron. Reason is, these are having negative charge. Electrons are having negative charge. This nucleus is with positive atmosphere. This nucleus is trying to attract charge. So there will be a force of attraction between this. Want to remove electron means we have to overcome these attractive forces. In this case, shell which is close to the nucleus has more attraction than which is next, and last shell has compared to less attraction. So removal of that electron is easy. Okay, removal of electron is easy means we, by using less energy, we can remove electron. So that is the story. Next one atom is in solid state, same atom is in liquid state and gaseous state. From which state we can remove electron easily? From which state we can remove electron easily? From gaseous state, since electrons are free in gaseous state. Okay. Now, so removal of electron the removal of electron, we need to apply some energy. We need to apply some energy. That energy is called ionization energy. For what purpose we are giving energy? To overcome the attractive force between nucleus and electron. This is called ionization energy. To produce ion, or whatever the energy we are using, that is ionization energy. Now I will tell you the definition of ionization energy. Important, students. Amount of energy required. Amount of energy required to remove electron from outermost shell of isolated gaseous atom. Amount of energy required to remove electron from outermost shell of isolated atom. Isolated means free atom. It is not in molecular form, or it doesn't have any bond. This is called ionization energy. Next, so we need to apply energy to get the electron. So ionization energy is endothermic. I will write, students, endothermic. I removed one electron from one atom. It will become monoionic state. For this, whatever the energy I used, that is IE1. Since I removed first electron. If I remove one more electron from unipositive ion, then it is called second ionization energy. If I remove third electron from divalent ion, ionization energy, third ionization energy, aluminum, writing E. A3 plus. Students, according to you, which ionization energy is more? IE1, IE2, IE3. IE1 for the removal of first electron we are using. IE2 for the removal of second electron. IE3 for the removal of third electron. Out of IE1, IE2, IE3, which is more? IE3 is more. Generally, IE3 is more. Reason is, once if it lose electron, nuclear power on valence electron will become more. Positive charge will dominate. Again, if you remove one more electron, again nuclear power on valence electron increase. So IE3 is greater than IE2, IE2 is greater than IE1. This is the order of ionization energy. And all ionization energies are endothermic only, no doubt at all. IE1, IE2, IE3, all are endothermic. Endothermic. All ionization energies are endothermic. Next, variation of ionization energy in a period group. Before that, factors I'll give. If we know factors, easily we can find out variations. Affecting ionization energy. First one is atomic radius. Important student. Ionization energy concept is very very important. Atomic radius. How it affects? These are all electrons, isn't it, students? So here, distance from nucleus to the outermost shell is this much. Distance from nucleus to the outermost shell is this much. In which case, we can remove electron easily. First case, because atomic radius is more. As atomic radius is more, or size of the atom is more, outermost electrons are far away from the nucleus. So nuclear force of attractions will be less. So we can remove electron easily. So from this, so easily we can remove electron means by using less energy only we can get the electron. So how it is affecting students? Ionization energy is inversely proportional to atomic radius. As atomic radius is small, ionization energy is more. So atomic radius is large, ionization energy is less. So in atomic radius we discussed first group to 17th group, atomic radius decrease, goes on decreases. So first group elements are having more atomic radius, So those elements are having low ionization energies, Among all the group elements, first group elements are having low ionization energy, so they are considered as metals. Metals are having low ionization energy since they readily loses electron. So larger the atom, smaller will be the ionization energy. Next, Z effective nuclear charge. Effective nuclear charge. As nuclear charge on valence electrons increases, instead of that nuclear charge only can write. Nuclear charge on valence electron increases, atomic ionization energy also increases. Nuclear charge on valence electrons increases means force of attractions are increasing. So to overcome the attractions, we have to apply more ionization energy, more energy. That is the reason Z effective is directly proportional to ionization energy. Z effective is directly proportional to ionization energy. As effective nuclear charge increases, suppose Al3 plus, Al2 plus, Al plus 1. Ionization energy decreases from here to there. Z effective is directly proportional to ionization energy. Next one, half filled or completely filled orbitals. Half filled or completely filled atomic orbitals. Generally, half filled or completely filled atomic orbitals are more stable. Elements which are having half filled or completely filled atomic orbitals are more stable. Example, if you take D5 configuration, half filled, D10 configuration, completely filled. If elements are having this type of configuration, otherwise P3 configuration, if they are having this type of configuration, they are like stable comparatively. They are stable. Removal of electron from stable configuration. If it lose electron, now it is in stable condition. If it lose electron, it will lose its stability. So in that case, atom readily it won't readily lose electron. Atom is not readily loses electron. So we need to apply more energy. Isn't it, students? If elements are having half filled or completely filled atomic orbitals, ionization energy is more. Important, students. Half filled or completely filled atomic orbitals are more stable. Removal of electron from more stable configuration requires more energy. So more stable, so they need more ionization energy. Elements with stable configuration needs more ionization energy. Example, if we see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Beryllium 1s2, 2s2. Boron 1s2, 2s2, 2p1. 2p2. Two P4. Other one 2p5. If you see nitrogen in last orbital P3 configuration has, P3 means stable configuration. Here also completely filled is there. Yes, completely filled. So lithium to beryllium it increases, but beryllium to boron decreases. The reason is beryllium has stable configuration. Next, out of nitrogen and oxygen, Oh, sorry, I did mistake. Out of beryllium and boron only beryllium. But in case of oxygen, again there is a exception. Here also P3 configuration. Here also P3 configuration. Half-filled configuration. This order they are asking frequently. Half-filled p orbitals are there, no? More stable. In case of beryllium, star mark you put. Beryllium and nitrogen case, with exceptional cases. Rest all cases it is increasing. Only in case of beryllium and nitrogen is more than adjacent element because of stable electronic configuration. Next one, penetration effect. Penetration effect. This penetration effect, if you consider in one shell there are S, P, D and F subshells. S, P, D and F subshell. Here S, because of its symmetrical shape, it will penetrate to the nucleus. Penetrate to the nucleus means it is very close to the nucleus. So removal of electron from S is difficult compared to P. P to D, D to F. So from P, D, F, complexity in their shapes increases. So the attractive power is there, no, that will be less. So that power is called penetration power. This penetrating power of S is greater than P, P is greater than D, D is greater than F. So penetration decreases. Decrease. Penetration power decrease. Now in one case, one atom case, electrons are in s orbital. Another case, electrons are present in p orbital. Which has more ionization resistance? S orbital. S orbital electron needs more energy because S is closely penetrate to the nucleus. This is called penetration effect. Penetration effect decreases from S to F. Applications of ionization energy. Applications of ionization energy. Applications of ionization energy. First application is to find out stable oxidation state. to find out stable oxidation state. How to find out stable oxidation state, students? Suppose M is one element. Its first ionization energy is just roughly I'm giving 50 electron volt. IE2 is 70 electron volt. IE3 is 210 electron volt or 250 electron volt. If you observe IE1 to IE2, there is no much difference. But 70 IE2 to IE3, there is a lot of difference. 3 times it became. Reason is, after losing second electron, it got stable configuration. Removal of one electron, removal of electron from the second plus what we say, removal of electron from di-positive state of the metal is difficult. From this we can make out. Means M plus 2 state is the stable state. Plus 2 is the stable oxidation state. So to find out stable oxidation state, what we have to find out? Where sudden jump observed, there stable oxidation means 70 to 210. Here second to third, there is a long jump, high jump in ionization energy. So second is the most stable one. Fourth and fifth, if we get plus 4 is the stable oxidation state. Plus 5 to plus 6, if we get much difference, sudden jump, plus 5 is the most stable oxidation state. Okay, to find out stable oxidation state. Okay, and metallic and non-metallic properties also we can find out. Metallic and non-metallic properties. So here plus I didn't do conclusion. No, plus 2 state is the stable oxidation state. Oxidation state. Next one, metallic and non-metallic properties. Metallic, generally metals are electropositive. They readily loses electron. They are readily loses electron means they have low ionization energies. So shall I write here directly? Low ionization energy elements are non-metals. Non-metals. Okay, this way we can find out metals and non-metals also. Next one, reducing agents and oxidizing agents. Reducing and oxidizing agents. See, reducing agent means reducing other substance. That can be done by donating electrons also, transfer of electrons also. So here, low ionization energy elements means they are ready to lose electron. If they are ready to lose electron, other element ready reduces. So low ionization energy elements act as reducing agents. Acts as reducing agents. High ionization energy Elements act as oxidizing agents, reducing agents. So reducing properties inversely proportional to ionization energy. If ionization energy is more, reducing nature is less. If ionization energy is less, reducing nature is more. Like that. Next, variation of ionization energy in a period and group. Ionization energy in a period. See, students, I told you atomic radius is inversely proportional to ionization energy. So across the period, atomic radius decreases. Atomic radius decreases means ionization energy increase. But there are some exceptions. I already had given the factors. So I am not going to explain it again. Just I'll give the points. Ionization energy increases from left to right. In a period. Reason is since atomic radius decreases. Example I am giving with exceptional case. Lithium, beryllium has more ionization energy than boron because of here completely filled configuration. Nitrogen. Again, nitrogen is more than oxygen. Fluorine. Neon. Noble gases, obviously, they are having high ionization energies because they already have stable configuration. In this order, they will give among the following which order is correct against the given property. Like that, they are asking questions. Next. In a group. In a group. In a group, atomic radius increases from top to bottom. So, ionization energy decreases. Ionization energy decreases because atomic radius increases from top to bottom. So lithium, sodium, potassium, rubidium, cesium. Even reactivity also depends on ionization energy students. If they are having low ionization energy, they are highly reactive. So, low ionization energy, they readily lose electron, they participate in chemical reactions also. So, cesium is highly reactive. Generally, first group, second group elements are highly reactive because of low ionization energy and more electropositivity. That factor, that property we'll discuss in the next class. So this is about ionization energy, students. Next one, electron affinity. Electron affinity. Here, ionization energy we discussed. Ionization energy, what we discussed? Amount of energy required to remove electron. Here, opposite. Here it is opposite. Amount of energy released. There it is required. Here it is released. Amount of energy released when an electron is added to outermost shell of isolated gaseous atom. Amount of energy released when an electron is added to the outermost shell of isolated gaseous atom. I'll write the definition. Outermost shell of isolated gaseous atom. See, here you may get doubt why energy is released. Negative charge is there, no? When you are adding, even that electron also having negative charge. Between same charges, repulsion occurs. Between same charges, repulsion occur. So energy will be released. In that repulsions, energy will be released. Between positive and negative, attraction will be there. At the same time, this additional electron, that what electron we are going to add, no, that will be repelled by inner electrons. Inner electrons. In that repulsions, atom lose some energy. That is only electron affinity or electron gain in enthalpy. So we can add electron to the outermost shell only. Next, from this, what we can say, electron affinity is exothermic. There, what did I say? Endothermic. It is exothermic. Since energy is releasing. EA1 is, but there IE2, IE3 also endothermic. But here EA2, EA3 will change. Endothermic. EA2, EA3 are endothermic. Reason is, once if you add electron to first electron to this, first of all it is getting repulsions. Again you want to add one more electron to the negative charge. Now entire atom atmosphere is in negative atmosphere. If you add one more electron, it will experiences more repulsion. to overcome the repulsions, you need to apply extra energy to add the electron. Means here we are using energy. So second, third, or higher, if you add still more electrons, this process will be endothermic. Here, one more point I want to give: how much energy you are using to remove electron, same amount of energy will be released when electron is added to the outermost shell. So from this, what we can write, IE1 is equal to minus EA1, or EA1 is equal to IE1 minus IE1. But better to keep minus for electron affinity 1 since it is exothermic. Understood, student? They may give sodium ionization energy is 5.91 electron volt per atom. What is its? This is ionization energy. Simply rough value, student. It is EA1 of sodium. If they ask, what we have to write? Minus 5.1. Only sign will change, magnitude remain same. Okay, students. These variations and all we will discuss in the next class. Thank you.